case for Mars. I'm going to just give sort of a brief introduction, and then we're going to go on to talk about some of the results of what we found out at this conference. The conference has been a two-day conference, Thursday and Friday. Pretty intense days. We started at 8 in the morning, and typically went till like 11 o'clock at night. Pretty much worked everybody to death. People are straggling in a little. Got some good results. We had a lot of good people from all over the country representing NASA organizations, industry organizations, private individuals from all over the country. A lot of diverse ideas, a lot of new suggestions, a lot of identification of problems that we didn't realize were problems. The idea of the conference, the concept of putting a conference on to look at the question of the case for Mars is sort of a natural thing to do for several reasons. One, because the shuttle was coming, going to launch. We had faith that it would make it. Mars, it looked like we needed another long-term focus maybe, and what we wanted to do, the purpose of this conference, was to see if Mars was an option for that long-term focus. We weren't going to come up with a detailed plan. It wasn't our intention at all. It was just to see if Mars could be an option for a long-term focus for both NASA and, say, the American government. The conference was organized by a student group here on campus, the University of Colorado Space Interest Group, of which I'm a member and the other organizers of the conference are a member. It was co-sponsored by several other groups, most of which you'll be hearing from will be represented today. Sort of the main theme of the way we've approached the question of why Mars, or the case for Mars, has been a theme of, well, what we want to do is not just go there, collect a few rocks and come back. But what has sort of become an underlying theme is that we want to establish, or we think that it's important to establish, a continued presence on Mars. That word, that phrase has appeared over and over again, often springing from independent sources within the conference. Continued presence, long-term exploration, long-term habitation, if you will. Continued presence. The model which we're thinking of is more like Antarctica, explorations of Antarctica, than, say, earlier space efforts, say Apollo. The model, an appropriate model, is Antarctica. Continued presence, a commitment to stay there and do research on a continuing basis. Doesn't mean we necessarily it's going to be easy. There's several reasons why it's a little bit easier on Mars than anywhere else. Mars is the only planet with an accessible surface that has an atmosphere. And as you'll see when we start talking about some of the scientific results of this workshop, that's a big plus. That's a big plus. There's a lot of scientific and engineering reasons why Mars is a big plus. And some of the people at the conference also considered some of the other reasons, how Mars could serve as a gateway to the outer solar system, how it might be more appealing, if you will, to the public. Mars has seemed to have a long history of public fascination, from War of the Worlds, John Carter, all the way up to the Viking results, and people thinking it looked like Arizona. I'd rather live in Mars than Arizona anyway. So I don't want to stretch this out too long since we're already a little late. And I'd like to go ahead and introduce the leaders, the people who were the leaders of the workshops, and are going to sort of report on, if you will, the findings of the workshops in their areas. So if I could get them to come down and sit at the table, I'll introduce them one by one. Well, coming down first is Stan Kent of the Viking Fund, and he'll be talking about spacecraft design. Dick Johnson of NASA Ames Research Center, who'll talk about life sciences, supporting man on Mars. Jim French of JPL, Jet Propulsion Laboratories, who will talk about mission strategies for getting to Mars. And Jim Oberg of Houston, Texas, who will talk about the social and political implications. And Jim Cutts, who will be here shortly, will talk about what do you do on the surface activities. So I think we'll go ahead and start with Dick Johnson, and let him talk about life sciences. Just turn it over to you, Dick.
Thank you. For a mission with men and women, what you have to do is support those people fairly carefully for the entire duration of your endeavor. So there are lots of questions that come up about how you keep people protected from environments that are more hostile than we're used to. I'm going to sort of break what I say into a few general areas. The first one has to do with medical things. It's generally true that in weightlessness, some things happen to your body. The blood tends to rise up to the upper part of the body, and you get lots of fluid in the top part of your body. Your heart gets a little bit deconditioned because it doesn't have to pump the blood up and downhill all the time. And some strange things start happening to your biochemistry. Your body senses you have too much liquid in it, so it starts eliminating liquid a little faster than usual, and you start losing sodium and potassium, things like that, a little bit more than you should, and your bones start dissolving a little bit very slowly. And it's not serious enough to have really impacted anybody, but it's for very long periods of time. People don't know whether it's really safe to stay in this kind of condition because it may get a little bit worse and worse and worse. Some of these things tend to level off, some tend to get worse with time. And we really don't have an understanding. Part of what we will attempt to do on Space Lab is to do experiments with people and with rats and monkeys, and to really get at all of these issues and get it all sorted out so that we have a good understanding of what's going on. In our discussions here, we're talking about a flight time to Mars that may be as short as 6 months, maybe a year and a half, but it is of a time scale that's comparable to what we've done on Skylab and what the Russians have done on Salyut. And we think that it's a reasonably safe guess that the people can handle the kind of medical situation I've been talking about without any problem. So what you could do if you wanted to is you could make some kind of a spacecraft that would spin and have an artificial gravity. And what we're saying is you don't really need to do that for trip times that we're talking about. If you were talking about people staying there for 10 years, staying in space for 10 years, then you might want to have a different answer. So I'm going to take most of the medical problems and just set them aside and say they're not significant enough that you build a very special vehicle. The one medical problem that is a little bit troublesome has to do with radiation. Once you get out of the Earth's low orbit, the 100 to 200 mile, beyond the Van Allen belts, then you're no longer protected by the Earth's atmosphere and by the magnetic shielding. And the radiation doses are significant. They're the kind of things that people who go into 3 Mile Island and turn off the valves get, but the kind of doses you're not allowed to get. And so the question is, what should you do about it? Well, you can do some shielding for the cosmic radiation, for the solar radiation that comes from the sun. We're talking about ionizing radiation, like from nuclear sources. And the sun gives off a steady source of these, and you can do some shielding. Now, every once in a while there's a solar flare, and for this you're going to have something in your spacecraft that allows the people to go into a shelter, maybe for a day or two, and get behind some material, like all your supplies. And you want to have a little hole in the middle of things where you can hide out for a day if there's an intense solar flare. Now, the worst part of the problem, though, it comes from the cosmic rays, the galactic things. And these are very high energetic particles, and you really can't stop them with any reasonable amount of shielding. They're so energetic that they go through everything, and they create what people call secondaries, and your dose is pretty bad from those things. And what's going to happen is you're just going to have to live with that. So the people who go will get zapped a little bit, and what happens really is that there's a slight increased risk from things like cancer, or there's a slight risk of birth defects and something like that in the future in your genetic material. But it's changing your statistics from 0.1% to 0.15% or something like that. It's a measurable risk, but you're not going to die of cancer. There's just one chance in 500 or something like that, more than you will, that you would. But there's not a whole lot you can do about it except provide the shielding for just the solar component. Okay, the next part I want to talk about briefly has to do with life support. That is, keeping people with air and food. Now, what we currently do here on Earth is we eat food and we breathe the air, and we pay for the food, but the air comes for free, and we breathe out carbon dioxide, and nobody worries about where that goes, and we take our waste and throw it in a hole in the ground. And it's kind of a cheap system except for the cost of the food. Now, in space you have to carry everything along, but that's still more or less what we do. We carry along a tank of oxygen, we carry along some food, we eat the food, generate some CO2, and throw all our waste away. And that's what basically the shuttle does. It does not save anything. What NASA's been working on for the last 10 years or so is a system that's called regenerative. That is, you don't throw things away. And you start tackling this problem piece at a time. The thing that you generate as waste that's easy to take care of is carbon dioxide, CO2. The carbon comes from the food, and the oxygen comes from the oxygen you breathe, basically. And if you could get that oxygen back out and separate the CO2 into C and O2, then in fact you could breathe that oxygen again. So that's the trick that these regenerative systems do. They do what they call carbon dioxide reduction, and they trap the carbon dioxide you breathe and give it back to you as pure oxygen in some kind of a machine that probably weighs maybe 300, 400, 500 pounds per person. But then you don't have to carry along an oxygen tank anymore because you're getting back. So for the longer you go, the more worthwhile it is to do this. Now also, you're wasting water. You drink water, there's water in your food, and you give it off as urine, sweat, and you also wash and do things like that. So there's wastewater associated with every person. And you can also think about getting that water pure enough again to do something useful with. You may be able to make it back into drinking water, or you may be able to take part of it at least and make it back into something that's suitable for washing your hands, something like that. So there are steps in water reclamation. So for the space flight portion of a trip to Mars, what we're saying is you do those kind of things. That is, you recycle your water, you recycle your carbon dioxide, and you would increase the efficiency of how you do business. Now, when you get to Mars, and if you're going to have people there with a continued presence, there comes a point in time when carrying all of your food from Earth is a very costly thing to do. I don't know whether we'll have an exact number of how much it costs to carry a pound of something and land it on Mars, but it's quite a big number. And so a couple of years worth of TV dinners for 10,000, for 10 people is going to be a lot. That's a lot of weight, and you want to begin to think about cutting down on that if you can afford to do it another way. So you then look at regeneration at one more level, that is in the food chain. So you begin to think about growing food on Mars. Now, when you grow plants, what happens is that the plants in our natural ecology use up carbon dioxide and give off oxygen. So that, in theory, you can just about balance out a person and the plant material it takes to feed it. One is using oxygen, the other is giving off oxygen, and vice versa with carbon dioxide. So you can shine a little light on a tomato patch and actually get some food and some oxygen and you can get rid of your carbon dioxide all at once. So that's the scheme we talked about. It turns out that if you want to involve meat and animal material in your system, there's a fairly big penalty to do that because animals aren't a very efficient way to make protein. They eat a lot of plant protein and they give you a lot less meat protein. And so you probably would think very seriously in a very constrained situation where you're trying to grow your own food of being vegetarians. And you want to grow plants that produce high yield and in fact are high in protein. And this means you're going to grow stuff like wheat, soybeans, corn, rice, and you're going to make that into as palatable things as you can. There's some tricks that you can do, like the Japanese do with miso, which starts with soy, but they ferment it and mess around with it a little bit, I don't know how, and make it into something that people like better than just eating soy milk. So you'll do things like that. So we talked about building a greenhouse. And the kind of things we don't know well enough now to tell you all the details is how efficiently you really are going to be able to grow plants on Mars. First of all, you have to get you have to decide whether you're going to use the soil or you're going to use hydroponics. Water is a pretty precious commodity on Mars. There's a little bit in the soil, there's a little bit in the atmosphere, but you have to work pretty hard to get that water. So it's probably unlikely you want big tanks of water to grow plants in. The dirt kind of comes for free, but it probably has some chemicals in it that you want to watch out for, so you might have to wash all the dirt once. But once you did that, you probably could grow things in it. How efficiently can you grow these plants? The kind of discussions people have is they look at what farmers are able to do, and then they look at what some people are able to do in greenhouses, and they begin to extrapolate this technology to a situation where you control every little thing you can think of. The temperature is just right, the humidity is just right, the carbon dioxide is just right, the oxygen is just right, and you make those plants grow as fast as they can. And we haven't really carried that process to its ultimate extreme, so you don't know how much better you can do than you can do here. But there are examples where people have tried this on small scales, and making plants grow 10 times better is not unreasonable for certain kinds of plants. So there's a little bit of a fudge factor you put in when you start calculating out your greenhouses. But it turns out that you've got a couple of football fields, and I won't be more specific than that, worth of greenhouse to keep your 10 people on a full, nutritious vegetarian diet throughout the time period. Now you're not going to build that in one day. It's going to take you maybe even a year or two, maybe more, doing that. So you're going to have to carry your food from the earth for that initial period. And in case your plants didn't grow, you probably carry enough food so that you have enough food to get back. But once you got that system established of growing plants, then in fact you then would be providing not only your food in a self-sustaining way, but you'd also be providing your oxygen, and you'd be taking care of your carbon dioxide. Now what we did in our own group is we looked at these things in a little bit finer detail. We talked about where the wastes go. We talk about the optimum pressures and gas compositions for people on Mars and for the plants and so forth and so on. It turns out that compared to us who live in California, you're already, from the point of view of atmosphere, halfway to Mars in the sense that you're breathing a lot thinner atmosphere than we do. And what you do on Mars is continue that trend. It would be like going up to the top of one of these mountains and living at that kind of atmosphere, except we probably put more oxygen back in so you didn't have to get so out of breath. But that would be the nature of what the atmosphere would be like. What the things we need to do in the future is sort of a homework assignment for the next year or two, is to figure out the real feasibility of providing the life support through a biological means, and to make the estimates more accurate. If it turned out that when I said a couple of football fields, it was really 10 football fields, and there are only 10 people there, and they've got to spend their whole lives in the wheat patch, that's not a productive thing, because they're there for other reasons. And on the other hand, if it turns out that it's a half football field, it's a very good idea. So what we've got to do is figure out those answers and home in on this. You also have to think about how you build it. You basically probably want to think about burying things in the ground to keep the radiation away from the people. So the people are probably going to be living underground or with 4 or 5 feet of dirt over their heads. But the plants, you have to let the sunlight in, so you have to think of windows. Mars is an extremely cold place, and you have to therefore keep your plants at a nice warm temperature, like in this room, while Mars outside, at least at night, gets extremely cold. So you're going to, every trick that you think you use here in Boulder to, in the wintertime, you're going to do 10 times over on Mars, just so you can conserve your energy. Your electricity, for instance, is going to be a very precious commodity, and you're not going to go around wasting electricity heating things if you can use the sunlight, conserve it by insulating glass and other things like that. So those are the kinds of things that need to be worked on to scale and size the endeavor and prove a little bit more conclusively that it's feasible to do it the way we said as opposed to feasible to do it another way. I think nobody doubts that you can't put the people on Mars and have them live. The real question is, how much cheaper can you make it by making the system self-sufficient and regenerative as opposed to carrying all your food from the Earth?
Okay. Do you have any questions for Fred?
You didn't say very much about electric power or power generation. That was choices. Do you have any ideas of which would be preferred or which would be not preferred?
Well, the way we approached the problem, Fred, was just try to stick to our discipline area. And as somebody who's worried about taking care of the people, we sort of tell folks down the hall that there's got to be an extension cord that comes out with electricity, and how you got electrons flowing down that extension cord, we don't care. So I'm saying it's a little bit out of my province. We did think about it, and I'm sure that that's going to be talked about by other people. But an idea that I'm enamored with is, in fact, using large solar arrays in orbit and beaming the energy down to the surface with microwaves, collecting it, and then making that into electricity. That's the concept that people have proposed for here on Earth, called the solar power satellite. And on a much smaller scale, it could be used on Mars. It may turn out that you have that electrical power at Mars from your space vehicles. So it might be a very feasible thing to do.
Let me just make one suggestion. The Canadians are working on a development called Slowpoke, which is an extremely small nuclear reactor, about 9 inches in diameter, whose purpose is simply not to produce electric power, but to produce hot water, close to the temperature of boiling, so not quite. And it's an ideal system, of course, designed for district heating. And it appeals to me that this could be a marvelous system for heating large areas of Mars, including agricultural settlements and communities.
I think the only problem people have is they don't know too much about space flight type small nuclear reactors that you can carry up and land and so forth and so on. And I think if people felt totally comfortable with those kind of things, they would propose them. And they will. They do.
Minimum model, you besides the food and no oxygen, is oxygen, is that true?
In theory, they're so close to being in balance that you...
Well, you get both for the same treatment.
Yeah, when you do one, you do the other, and then you got to do a little fudging to make them keep balance. But for the first approximation, they're the same.
How does the radiation compare to CO that you do for the secondary?
It is certainly true that, okay, where there is a greater risk of living in Denver than there is in Colorado from radiation because you have that much less air over your head to shield you. And I think that's a well-known fact. It's also true of people who fly airplanes. Airplane pilots are getting a higher dose than other people. And if you're there continuously, it's not nothing to worry about, but it's a fact of life. People who live in this area obviously have accepted that risk.
That's what I'm getting at.
But it's like, it's like 1/100% on a mortality curve. It's not you're
Put
going
it
to
in
die.
appropriate context here, you do take the risk for it. Living here is one of those things.
Right. And so living on Mars is like, 10 times worse than living here. Something like that.
You said you're gonna have 2 football fields and stuff and 10 people. Are this all gonna go in the first trip, or is it gonna be continuous supplies, or how all of a sudden they get up there?
Well, we sort of said you'd make some greenhouses there. But, and that means you're going to either carry some plastic with you, which is maybe not a good idea, it's hard to say, because the ultraviolet light on Mars tends to degrade plastics and rip them up. So what you might want to do is have a small glass factory that can actually take rock and process it through some processes and actually turn out panes of glass. Over a period of a year or two, you make a lot of glass, build yourself some holes in the ground, and seal up the tops with the glass, and make yourself some sort of half underground greenhouses. Now, I know that's really feasible, but that's sort of the primitive notion we at least think about first.
Okay, we'll go ahead and go to the next.
If you have if you put large plastic beanbag factories and separate your garden pieces, would that break up would the size be worse because of the smaller pieces? Would the total area be worse?
I'm sure you lose some efficiency. You want it.
Not as a total system.
No. You can break it up in pieces, but I'm not sure how small the pieces can get before you don't want to make them any smaller. But I think ordinary greenhouse size is probably about as small as you want to go. So the bean bags would have to be purchased. Yeah, they wouldn't be this big, but they'd either be tens of feet or hundreds of feet in that range.
Okay, Jim French from JPL will talk next on mission strategy.
As Chris mentioned, of course, the focus of this conference was the establishment of a permanent manned presence on Mars. And for the most part, our strategy deliberations did address that, the simple how-to of getting a permanent manned base on the surface of Mars. However, it was definitely brought out in the course of these meetings that there are some considerations that must be dealt with before you can commit yourself to this kind of an operation. Clearly, one of the considerations has to be whether there is a Martian ecology. Now, we have, from the limited information that the Viking landers have provided us, we don't have any strong indication that there is. However, we certainly cannot say that we have any unequivocal evidence that there is not. And should we, at any time, find evidence that there is native Martian life, that there is a Martian ecology, then we certainly would have to give some serious question to the effects of a Mars base or a colonization program or whatever on the indigenous Martian flora and fauna, if we can use those terms. However, finding answers to those questions is not incompatible with what you have to do to prepare to set up a base on Mars anyhow. Because clearly there has to be a data gathering, what I have chosen to call a reconnaissance phase. Now, you may say that we've already done a bunch of orbiters around Mars and put down a couple of landers. Why do we need more? My response to that is that we do not. If your only goal is to simply go to Mars and land and come back, bringing back some samples and saying, look, we did it, we went to Mars. We have the adequate engineering and environmental information to be able to do that now. However, if our prime goal is a long-term manned presence on Mars, then there are some things we need to know. As Dick implied, setting up such an establishment on the surface of Mars is not going to be easy. You want to put yourself down at the optimum location to give the best shot at being successful. We do not have the information at this point to know what that optimum location is. There's clearly a reconnaissance phase that is essential. In my estimation, if you did not do anything else, you need to address the question of the location of water on Mars. We know there is water there. We know there is water on the surface in some quantity in the permanent North Polar Cap. We strongly suspect that there is a lot of water beneath the surface in the form of permafrost, and even some evidence that, at least in the area called Solus Lacus, that there may be liquid water a short distance beneath the surface. But we don't have enough information to unequivocally say, yes, we want to go there and put our base there. We need to explore further to get a good handle, as I say, if on nothing else, on where we can find adequate supplies of water. And I'll talk a little bit more about why that's so important. But to do that, you at least need an orbiter that, by various remote sensing techniques, addresses that question. It would be desirable to supplement that orbiter with devices called penetrators, missile-shaped projectiles that penetrate beneath the surface up to several meters in some cases, and can actually do direct analysis of the soil constituents in their vicinity. More than that, you would really prefer to have a full-grown geoscience orbiter, which would do the atmospheric science, look for the volatiles, as well as giving you detailed mineralogical, geophysical information, and more detailed maps even than the ones we've already got. The question, of course, is whether you can afford to do all this, which is why I kind of presented it in terms of a shopping list of options. The ultimate, of course, would be to do a thorough and detailed unmanned exploration of Mars before you ever committed to a manned mission. That would involve such things as autonomous rovers on the surface, possibly airplanes, which are feasible at Mars in spite of the thin atmosphere, and a series of sample return missions from selected localities. That would allow you to get things really nailed down about as well as you could hope to do so before committing to the manned mission. I guess I personally am not strongly in favor of doing the whole thing before you do the manned mission, but you could get into a lot of debate on that. I simply present it as a list of options which one might undertake. Once, however, that you have completed this reconnaissance phase, and I will reiterate that I consider at least an orbiter that looks for volatiles, basically water, as mandatory before we try to set up a base. You want to select the site based on the information that you've collected. There are a series of criteria that we came up with. The first one, I'll present them in order of high, medium, low priority, our estimation thereof. The first one seems awfully obvious, but you really have to think about it, and that is accessibility. Can you conveniently get to the location on the surface using the entry vehicles that you've got, given the approach geometries of the interplanetary trajectories and so on? It depends heavily on what hardware concept you use to implement, or that you have available to implement the missions. Highly maneuverable entry vehicles, very high energy propulsion systems, essentially open the whole planet. On the other hand, if you are severely restricted in your propulsion capability or the maneuverability of your entry systems, you may find yourself limited to certain areas on the surface. The next one, in importance, in my estimation at least, is the presence of the necessary raw material. Now, the first one in line is water, because you can use that for manufacturing your return propellant. You can use that with your life support functions. You can use it to hydrate the freeze-dried food that you're going to bring with you from Earth until Dick's farms get operational. Water is crucial to the establishment of the base, because you have to bring it all with you and you have to recycle it. And more particularly, if you have to bring all the propellant with you that you're going to need for bringing people back when their tour of duty is over and so on, you're putting a crushing burden on your transportation system. There may be enough burden to prevent it from ever coming to pass. Low elevation of the surface site is not mandatory, but it's highly important, because the lower your elevation, the higher the atmospheric pressure, the easier it is to affect the landing, the less penalty there is on propulsion, because you can make better use of aerodynamic drag to get you on the ground. Furthermore, it's easier to pressurize the atmospheric gases for use in the farms and propellant manufacture and what have you. It doesn't sound like much, but every little bit helps. Of less substantial priority is a location with easy communication with Earth. Obviously, you want to have communication with Earth, but if everything else drives you to a site that, say, is in a high latitude polar region, which will, for some periods, be out of sight of Earth, you can always get around that with relay satellites or something of that nature. So that's kind of a low end of the high scale, I guess you might say. The availability of solar energy is a moderate priority. We would certainly like to have it available, either in terms of solar arrays on the surface or in a position which was suitable for the kind of power satellite operation that Dick was talking about. That basically tends to mean low latitudes. There are, as I said, reasons why you might want to go to the poles, predominantly the availability of frozen water on the surface. If so, there are other alternatives for power, as was mentioned, nuclear being the obvious choice. So solar energy availability is the best immediate priority. Science interest is of a medium priority as well. You're clearly going to want to do a lot of science exploration and experimentation on Mars. But once you're there with rovers and airplanes and what have you, you can pretty well go anywhere you want to on the planet. And while it would be nice to be situated in a scientifically interesting locality, so you wouldn't have to travel to do your experimentation, it's certainly not mandatory. Finally, sort of a low priority is that it's helpful in launching from the surface of Mars to take advantage of the planetary rotation, which pushes you in the direction of a low latitude launch site, preferably on the equator. However, if you are manufacturing your own propellants and so on, that is pretty much of secondary importance, so we didn't consider it a high priority driver. Wherever you decide to land, and this addresses the question that the gentleman over there asked, before you commit your crew, you're going to want to have stockpiled at Mars a substantial portion, if not all, of the equipment that's required for setting up your base. We concluded that since there is a possibility, even though you will have selected your primary landing site beforehand, you might, as happened in the Viking program, get there and find that for some reason you can't use that site after all and you want to go to a secondary choice. That tends to preclude the idea of stockpiling the equipment on the surface prior to the crew arrival. We concluded, therefore, that you'd want to put the equipment in orbit. How you would get there, we did not specify, because there are a variety of options depending on technology developments over the next few years. You'll hear people talk, or we have heard people talk about solar sails, solar electric propulsion, technology which we call aerobraking, which is kind of a low technology controlled atmospheric drag to get into low circular orbit. All of these are applicable as unmanned freighters to get your equipment there. And and indeed freighter versions of the vehicle that will carry your crew there, be they propulsive ballistic vehicles in the manner of the Viking orbiters but bigger, or whether they're more exotic aerodynamic capture vehicles that use atmospheric braking in the atmosphere to achieve orbit, or indeed more new high technology concepts such as mass drivers, fusion technology, or what have you. There are so many options that we chose not to specify one, but simply to mention these choices, because all of them would work. The exact optimization of the manner in which you get there would vary depending on which of these options you care to implement. In any case, you would presumably use a number of vehicles. Critical items would be redundant. You'd take plenty of spares, in essence, of things that you simply couldn't get along without, because there's no way to run back and get one more once you're there. Manifesting amongst the different vehicles would be important. Make sure that you didn't put all your crucial eggs in one basket and then have somebody drop the basket. So that's going to be a very important planning exercise. Things that you might stockpile ahead of time would be some sort of erectable shelter, consumables for the crew, extra propellant, science equipment, construction equipment, local devices to land all this stuff, whatever might be the chosen mode of doing that. Resource extraction equipment to make your propellant, to make additional oxygen and what have you, just to gather the water and break it loose from however it's bound into the soil. Exploration vehicles, airplanes, rovers, what have you. And finally, selected raw materials, and structural materials, foam in place plastics for insulation, beams, sheets of aluminum, and other structural materials that somebody put at the hammers and nails and 2x4s that you need to put the base together. And then finally, the energy source, whichever one that may be of the options that we've discussed. Once that equipment is there, you commit your first crew. They would, once they arrive in orbit, by whatever various means, they would do a final verification of the landing site. You would then land a beacon or beacons for navigation to allow your cargo vehicles to find accurately the chosen location. Once the beacons were down and functioning, you would then land the equipment. Given highly maneuverable entry vehicles based on modern technology, beacons on the surface, your landing accuracy could probably be on the order of a kilometer or so. So you certainly wouldn't have to travel all over the country looking for the pieces. Once the equipment is down and landed, you would commit the crew. After they got through with the ritual call from the president or whoever, they could then proceed with business of surveying the site, setting up the initial base, and getting it functional. Verifying the functionality and habitability of the base would be the prime first goal. Once that's done, and once you're sure that you're safe for a while, then you can indulge in the science, set up your science equipment, and start your exploration and your resources extraction, set up the farms, that sort of thing. Somewhere down there, you have to, as it's fashionable to say these days, bite the bullet, because there is a particular launch window for that crew to come home, and you would provide that first crew with the capability to return home, even if the propellant manufacturing and all that didn't work. If they miss that window, then they've got to stay there till the next one rolls around, which might be a couple of years downstream. So there's a real crucial go, no-go point, by which time that base has to be fully operational and capable of supporting those people until the next departure opportunity, which also means the arrival of the next crew. The follow-on missions, in essence, would be analogous on a large scale to the way the Russians have been resupplying their orbital space station. Crew rotations on short flight time opportunities, and as frequently as we could do it, unmanned resupply missions to bring in the crucial stuff that you can't make in a first level Mars base, the things for which you're still dependent upon Earth. The goal would be to expand the number of people, expand the base capability. Again, logistics is a major factor in all this. And keep the propulsion, keep the total requirements of the mission down. It depends critically on propellant manufacturing on Mars using indigenous atmospheric and water. But you can, once you establish the sequence, you can trade return vehicles. The incoming crew brings the new one, and those who are ready for rotation go home, and the old one, very much analogous to the Soyuz series. There is a need, I think, for some rapid transit options to get crucial equipment to Mars as fast as possible in a matter of 2 or 3 months. You can do that with basic propulsion systems that we already have for a minimal payload, taking advantage of atmospheric braking at the other end. You can't do it just any time, but it can be done. And it's nice to know you do have that option if you need it. The goals for this base, maybe I should have touched on that at the beginning. The goals for this base really, I guess I did talk about it actually, but are to evaluate Mars as a long-term habitation for man. That's what it's all about. However you implement your technology to get there, that'll be your primary focus. Now we have taken in this the assumption of relatively modest improvements in current day technology in order to do this, to demonstrate that it does not hinge upon a great breakthrough. Now, developments of new technology, particularly in propulsion, for example, fusion, or some other very high energy technology, would enhance this enormously, cut down the flight times, make the whole thing much easier. But the point to be gathered here is that you don't have to have it. You can do it with what we have available right now. With that, I think I'll close and I'll take any questions.
Do you have any questions, Jim?
This sounds like it's gonna cost at least as much as the moonshot program.
Uh,
Wrong time to answer those.
no, it's a good time for the question. You want to answer that, Jim? Or?
Yeah. The costs have been discussed. You won't hear that presentation this morning. The general consensus is that for just a minute, you got to be careful on what you compare. To just do a mission to Mars to sample a locality and bring it back using a manned vehicle. The consensus is, I think, that it probably would cost substantially less than Apollo did. Maybe half. You debate about that, but hardly anybody seems to think that a current year dollar is, I shouldn't say that. There are people who will tell you it'll cost $100 million to do it. Most people, I think, around here are convinced that it will cost less than that. The reason being is when we started the Apollo program, you think back to 1961, what we had was a few ICBMs that didn't work very well and designed for a capsule to set on top of one of them to go into orbit. What we've got now is a very broad base of technology in space operations, propulsion, guidance, attitude control, and so on. There's some work that needs to be done, certainly, but we're not starting from ground zero this time. Now, the exact cost of a major program like I just described, where you're trying to establish a substantial base on Mars for permanent habitation, I can't tell you that price. It's clearly going to cost more than just the one-off mission to go there and do some scientific exploration and come back. But it's not going to take the national debt either, contrary to what a lot of people would have you believe.
Any further questions? Okay, we'll go to the next speaker who's going to speak on spacecraft design. He's Stan Kent, who's also director of the Viking Fund, one of the co-sponsoring organizations. And later on today, he's going to talk about what the Viking Fund is and what its implications are. I think that's going to be a very exciting talk later today. I don't mean to imply that the one he's going to give now isn't going to be exciting, but we certainly wouldn't miss the one this afternoon.
I'll give you a commercial also. We're talking about going to Mars and walking around. I don't know how many of you know what's on the program later this afternoon, but we're going to be showing Mars in 3D, where you wear the red and blue glasses. And if you let your imagination roam and you've had enough wine to drink at lunchtime, you're going to believe that you're walking on the surface. And so that's the commercial. And if you've got any friends out there that want to have a walk on Mars this afternoon, go out there. We'll put the 3D glasses on and walk around campus, and I bet you'll have a real good crowd in here. But on to spacecraft design. Spacecraft design was a real difficult thing to pull together because you have so many influencing factors, and everyone looks at you and says, well, what does it look like, and what does it do, and how much is it going to cost? And those of you that have ever been involved in spacecraft design know that you never design a spacecraft by committee. And so we immediately said, we're not going to come up with concrete designs, more concepts. We don't want to tag exact numbers on them, but sort of point in general directions and identify problems. So those of us that are dedicated and have ways of finagling computer time and things like that can go away from here and come up with some more definable approaches over the next year, so that when we get together again for another case for Mars, we'll have a little bit more of a database and know where to go. And so that was what we were faced with. Come up with the spacecraft that would do this first step towards a colonization mission. We didn't pretend to attempt to look at the precursor missions, the robot penetrators, the orbiters. We wanted to look at what would send the people there. And so you split that into a couple of categories. You have the crew transport vehicles, you have the freighters, and then there's the rapid transit vehicle, which Jim talked about. We didn't look too much at the rapid transit vehicle. We wanted to concentrate more on basically the basic goal of the conference, which was just plopping the people and the freight down on the surface. And many, many thousands of words were exchanged on propulsion schemes, on ways that you could house the people, trip time versus consumables. But there's an old adage that a picture is worth 1,000 words. So rather than go through the many, many thousands of words, and some of them I wouldn't want to repeat here, we're going to show you some pictures. And I really got to give credit to the two people that did this, Carter Emmart and Paul Hudson. Carter's with the space working group here, and Paul's with Disney Productions. And they stayed up most of the night putting some artist concepts into all those words and all those numbers. And so I'm going to use those to give you a little bit of a glimpse of a spacecraft designed to Mars. And these things are as sticky as anything, so please bear with me. Let's see if we can get this. Let me play with it, getting this right for a minute. What this represents is our concept of a cargo carrier. And there's many ways to transport payload in space. One of the things that your fundamental limits of chemical propulsion is that you measure performance, if you will, engineers measure performance in terms of something called specific impulse. And the limits of chemical propulsion are around 470 to 500 seconds. If you look one step beyond that, at something like electric propulsion, you're in 3,000 seconds. It's order of magnitude better. So we took a quick look at how much chemical propulsion would it take to send huge amounts of payload, like 200,000 pounds of payload, to Mars. And we quickly said that you've got to have a lot of propellant up there, literally something like almost 1 million pounds of liquid oxygen and liquid hydrogen to transport that 200,000 pounds. We thought that really is not that good, because you've got to get that propellant up there somehow, and the only vehicle that we were going to rely on over the next 20 years to do that is the shuttle, and a shuttle-derived vehicle. And so we felt that one of the reasons why the cost has been so high for manned Mars missions has been the number of launches that have been involved in getting your stuff from the Earth's surface up into Earth orbit. So one of the overriding philosophies we took was, let's see if we can minimize the amount of Earth to orbit operations. Let's see if we can use some of the stuff of the shuttle system for our benefit. And Tom Taylor, as one of the participants in the workshop, has done a great amount of study of using the shuttle's external tank. And you'll see a film of that later this afternoon. The big liquid oxygen, liquid hydrogen fuel tank, carrying it on into orbit and using it as a habitat, as a workshop. And we looked at using it as a way of getting things to Mars. And one of the crucial propulsion devices that we thought was essential is something called solar electric propulsion. And that's sort of what you see, those big arrays. They're big solar arrays that collect energy from the sun, convert it into electricity, and use that to ionize a propellant. And we started off looking at mercury. That's the standard solar electric propulsion propellant. Gives you something like 3,000 seconds of specific impulse. You then shoot out that ionized mercury, very high exhaust velocity, something like 30,000 meters per second. That's where you get your performance from. We felt that that offered a lot of promise. We also looked at a little bit at solar sails. Solar sails tended to give you a little bit longer trip time, but we felt that we could not in this workshop here differentiate between the two. And what I think you'll probably have is a hybrid system. Solar sails used for maybe low priority freight, maybe solar electric propulsion for a little bit more high priority freight and people perhaps, and then this rapid transit thing for the emergencies. And that's one of the things we wanted to get across, is if you're going to do this, you're going to do it in very much the way that you did a railroad, that you did a airline transport fleet. We're not going to sort of fly from here to Tokyo with just 707s. You're not going to fly from here to New York with just 747s. You need the 727s, the 737s, the 747s, and you need the Cessna 172s and the Learjets. That was sort of the approach we took, a whole fleet of vehicles. And I'm going to show you some of those concepts right now. But anyway, this was the transfer vehicle for transferring bulk payload and freight in there. And this basically got a cone that's hollow. You've got a hollow circular hole right through the cone. And you've got all your farm equipment, your food, some of your propellant that you'd use from getting back up off the Mars surface. And this thing would be assembled in geostationary orbit above the Van Allen belts and would basically spiral out, take something like 12 to 16 months to get there. And once it got there, go into orbit around Mars, perhaps at a later date rendezvous with one of the moons of Mars and use that as a supply station. There's two moons of Mars, Phobos and Deimos, and they offer exciting resource potential. There's a lot of good stuff we can use there. Basically, this is where we thought we'd get freight there. Next question is, how do you get the people there? This is what we sort of came up with. We looked at the external tank and said, here's this nice big hunk of metal, this big tin can that's currently being taken to 97% of orbital energy and being thrown away. Now, for a loss of a certain amount of shuttle payload, you can carry it on into orbit, rendezvous it there, keep it in a stationary orbit, then retrofit it, and we thought it would take something like about 4 shuttle launches to retrofit the vehicle to make it habitable, to put the scientific equipment in, to put the regenerative life support systems in, to put all the nice cozy things the crew's going to need, the padded rubber walls, things like that for when they get a little crazy. And this thing that you see down here is what goes in the hole of that cone that I first showed you. This is the ascent stage and the descent stage for the crew. But that goes into the cone and provides the propulsive energy for landing on the Mars surface and then for coming back up. We felt it was important to carry this with the crew because if you're not sure that you've got that way of getting down there, you may have to abort the mission. And if you haven't got the way to get back, you may have to abort the mission. So we felt that this should go with the crew for constant checkout during the in-transit time. Now, it may turn out that the solar electric propulsion device with Mercury does really take way too long to get the crew there. we defer that to the people considering in transit time what that does to the crew. But we have to say, is a 12-month trip time acceptable? Is a 16-month trip time acceptable? But we address that a little bit later, saying, how could you improve some of these propulsion devices with what we've got at Mars? And I'll describe a scheme later whereby we could really improve the propulsive efficiency of solar electric propulsion. That's basically how we get the crew there. Huge solar arrays, radiators. These solar arrays we sized for something like around 500 kilowatts of energy. To give you an idea of what a growth that is, the current solar electric propulsion stage is envisioned for doing exploration of comets and asteroids and things like that is around 30 to 25 kilowatts. And so it's an order of magnitude growth beyond that. And that may present a problem. But what we wanted to identify were pacing technology areas that you could start work on now, or that if we had to identify roadblocks to landing people on Mars, that people could work on in the labs here and now, that we could give action items to NASA or to industry and say, hey, this is a crucial problem, can you solve it? One of the areas that needs to be solved is that array technology. And one of the things we'll be going away doing is trying to look at an actual trajectory to Mars in terms of the coast time, the number of thrusters that you need. Is that an excessive propellant requirement? What we came up with is that you need something like around 114,000 pounds of mercury. Now, that translates to about 140 cubic feet of mercury. There's more than enough space in the external tank for that, but the question is, and maybe somebody knows the answer out there, is there really that much mercury on the planet? I mean, have we got enough mercury to send one spacecraft to Mars? And if that's a problem, there's a way out of it, and actually it's a beneficial way, and that is that if you can't propel your solar electric propulsion stage with mercury, another desirable propellant is argon. And if you look at one of the proposed systems, advanced solar electric propulsion stages, you can get quite a vast